Welcome you all to this course on electron diffraction and imaging. In the last class, we talked about one of the new techniques in which has come in transmission electron microscopy in recent times, namely scanning transmission electron microscopy and C contrast microscopy. These are all the two techniques which we have talked. In today's class, we will talk about analytical electron microscopy. There are many microscopes are there where in addition to getting information about the microstructure of that sample, we can get information about the composition at different regions of that sample, okay, with very high accuracy. What are the advantages of it compared to that of other techniques where we can get composition like SEM and EPMA? We will also discuss that, okay. But mainly we will talk about button. I mentioned in the last class that when the incident probe is an electron and it enters into a sample which is very thin, okay, secondary electrons are produced in the material, backscattered electrons are produced, X-rays are produced. These are all because of the interaction of the electron with that sample. Then the electrons are diffracted. These are called transmitted electrons. Then elastically scattered electrons are there. This is what we use for C contrast microscopy. Inelastically scattered electrons, which are the ones which are used for energy loss spectroscopy. What is essentially important which one should understand is that when we have a very thin foil in which high energy electrons which are accelerated to maybe 100 keV to maybe 300 keV, energy electrons are falling on the sample and the thickness of the sample is of the order of maybe less than 50 nanometer, let us say that. As the beam passes through the sample, most of the electrons comes out without losing any energy, or these electrons are essentially elastically scattered. Okay. But in addition to it, a few electrons lose some energy by interacting with some of the atoms which are present on the sample. This is a statistical process. For each of these interactions, there is some cross section which is associated with it. On the basis of the cross section, we can tell that if this is the incident beam current which we use it, or this is the total number of electrons which enters. Out of it, maybe only this much fraction will interact with the atom, okay, and give rise to these scattered electrons. The first thing is that when we said that electron interacts with that sample, okay, and various types of electrons are produced, okay, and what are the types of interactions which are possible? One of the interactions which is called as a plasmon interaction. What is a plasmon? Especially that sample, if you consider a crystalline or a non-crystalline sample, it does not matter. There are ion cores are there surrounded by electrons which are there, okay, which are uniformly distributed in that sample. Okay. When the primary beam with this energy enters into that sample, it scatters or imparts some energy to some of these electrons. Okay. These electrons are deflected from their original position and this gives rise to some charge imbalance, okay, and the whole these electrons starts oscillating and decays and comes back to their original position. These sort of oscillations are called plasmon oscillations, and the time scale of this operation is of the order of femtoseconds. Okay. The energy which is being transferred to these electrons is generally of the order of 10 to 20 electron volts. Okay. So this is one of the process by which the electron loses some of its energy. The primary electron beam in a microscope loses some of its incident energy. The other way in which the electron loses energy is by phonon scattering. That is imparting some energy to atoms which are vibrating in the atom, but the energy of these phonons is of the order of it is less than 0.1 electron volt. So, this energy is differences is normally not very difficult to measure in a microscope, or the when we have 100 or 200 keV electrons, this sort of energy loss is not going to make much of a difference. Other than that, what it happens is that the electron can the primary beam, when it has very high energy of the order of this energy, it can knock out electrons. For example, if it is a copper, the sample is a copper based sample, okay, then it can electron from the K levels, which require around only about 8 to 9 keV of energy, okay. And when electrons having such electrons are knocked out from such levels, which we will be talking about later, the atom will be in an excited state. It will come to the ground state by lot of radiative processes, which are essentially characteristic X-ray emission or Auger electron emission, okay. This especially the character these two processes could also be Auger, and the characteristic X-ray could also be used for chemical identification of the elements, okay. Then secondary electrons are also emitted from the sample surface, okay, where the energy of the secondary electrons are less than 50 keV, 50 electron volts, 50 L, that is secondary electron energy is. For these are all the various processes by which primary electron beam loses energy as it passes through the sample. What will be the consequence of this sort of interaction? Immediately one can make out that when it loses energy, when the electron comes out, we have some electrons which have not lost any energy. There are some electrons which have lost some energy. Because of that, there is a variation in the wavelength of the energy of the electrons, and consequently there is a variation in the wavelength of the electrons. Well, and consequence of this wavelength of the electrons or the energy spread in the wavelength, okay, gives rise to increases the chromatic aberration, okay. This brings about the loss of resolution of the images, that is the resolution becomes poorer, okay. Let us look at what is the cross section for these various reactions, okay. Here what is being done, this is, you know, the cross section is given in meter squared. We have discussed about cross section in some of the earlier classes when we talked about atomic scattering factor, okay. This is for plasmon losses, the cross section is around 10 to the power of minus between minus 21 and 22, okay. This is for secondary electron emission, the cross section is 10 to the power of minus 25, and this is a function of beam energy which we are plotting it, and this is for K shell ionization, this is for L shell ionization, okay. This is for elastic scattering of the electron, what is going to be the cross section. So, if you look at it, the plasmon loss is the one where the which has got a maximum cross section, okay. Then comes elastic scattering, then is K and L shell ionization of the material. Secondary electron emission, the cross section is extremely small, okay. Now, let us look at what is the sort of interaction which takes place when an electron is entering into the sample. So, when the primary beam enters into the sample, since it has got a very high energy, okay, it can penetrate, that is, there are electrons are, this is the positive charge, electrons are there in various levels. The primary beam could be entering here, anywhere it is, okay. Suppose it is coming very close to this electron, which is a K electron, that shell. When it comes very close to it, okay, in the process when it comes from here to here itself, it can lose some energy interacting with the outermost electron. even then the energy which is lost is very small. It has sufficient energy to give it to this electron which is there in the k level. So, this electron, okay, if it has got sufficient energy, it can be knocked out from this level depending upon the energy which is required. There is a minimum threshold energy which is required. That energy is the one which is required for the electron to be knocked out from here and brought to the outermost shell or the vacuum outermost level or the vacuum level, okay. Or if the energy is more than that, it can be knocked out from the atom itself, okay. When an electron with this energy is knocked out, okay, the atom is now in an excited state. To come to this ground state, that is what essentially is being returned. This could be done by either X-ray photon, or it could happen that with that incident beam itself could be an X-ray photon, or it could be an electron. In this particular case, we are considering the electron, okay. When a vacancy has been created in this k level, an electron from this L level or from the M level or any of the above levels can come down to fill the vacancy in this level, okay. And the electron in this level is the one which is going to see this difference, see the vacancy which has come in this level, which is able to fill it. So, this will come down, okay, and giving rise to an X-ray photon, okay. This X-ray photon, if you see that energy of the X-ray photon is essentially the difference between these two levels, EL minus, that is H nu equals EL minus EM, or equals EK minus EL, okay. This depends upon what is the sort of transition which is taking place. When an electron with this X-ray with this energy comes out of the sample surface, okay, this characteristic X-ray we can measure it, and this is counting the number of X-rays with this energy is coming out, we can find out what is the concentration of that element which is going to be there in that sample. This way we can find out the composition of the sample. Okay, this technique is used in SEM. Okay, this technique we use in electron probe microanalysis. Okay, this technique is used in TEM as well. Okay, especially in analytical electron microscope, it is being used. Other process by which, and there are some rules which are governing this emission of these X-rays. The transition rules are there which has to be followed, and using either wavelength dispersive detector or energy dispersive detector, these X-rays could be generated, which we will show later. Okay. In addition to it, okay, when an, the other alternative process by which this decay can occur from excited state to a ground state is that when a vacancy has been created in this particular level, okay, we said that an electron from a higher level will come down to this level, for example K alpha 1, this comes down to this level to fill the vacancy and X-ray is generated. Assume that instead of it, this energy is used, that is this electron comes down and instead another electron is emitted from a higher level which requires very small energy. That means that this energy which is available is used to knock out an electron from another level. This transition is called as a radiationless decay, okay, radiationless transition. So, then the energy of this electron will turn out to be Ek minus El, okay. Suppose the energy of the electron to this particular level, M level is Em, okay, minus Em. This is what is going to be the kinetic energy of this electron. Okay. These electrons are called as Auger electron, and for this discovery for Auger in 1925 he was given the Nobel Prize. Okay. So, essentially these are all the two processes. So, this Auger electron is also characteristic of the element. Okay. So, by measuring the energy of this Auger electrons, we can identify what is the type of element which is present on the sample surface, and from looking at the integrated intensity of the peaks, we can find out what is the concentration of the element in the sample. since we are using electrons, okay, as I mentioned here, as the electron enters into that sample, it starts losing energy before it interacts with that atom. What it essentially means is that either it can lose some energy, okay, and then come and knock out an electron from this level, or it can so happen that it has not lost any energy and it has the full energy it has reached, and part of the energy is used to knock out an electron from this level to the vacant level. Now we know the energy which it has lost. If the primary energy of the electron beam is E0, E0 minus Ek is what is the energy with which the electron will be coming out of the sample surface. If an electron comes out with this energy, okay, this energy is also characteristic because a definite amount of energy which has been lost, characteristic of the element from which it has lost the energy, okay. And if we measure the kinetic energy of these electrons, this could be used to identify the elements which are present on the sample surface. That means that the primary energy has lost some energy loss, okay, and this energy loss has been used to find out the composition as well as do a quantitative analysis to find out the concentration of elements in the sample surface. So, this is called as electron energy loss spectrometry. Okay. One of the important advantages of electron energy loss spectrometry is that even for either X-ray emission or an Auger emission, okay, vacancy has to be first created by knocking out electrons from the various core levels has to be done. Okay. This process is always going to occur. Okay. Since this process has to occur, okay, we can use this technique, okay, is sensitive to all the elements which are present, okay, irrespective of their atomic number. So, even light elements could be detected using this particular technique. Okay. We will come back to it in a minute. Okay. Another important factor which I mentioned is that there is a probability that as the electron enters into a sample, it loses some energy. Suppose it has lost sufficient energy, it has not sufficient energy to knock out an electron from this, okay, this will contribute to the background level. Okay. That means that even if it has lost some energy, to knock out an electron from this level, some minimum amount of energy is required. Okay. That energy is called as an over voltage which is required. Generally, if the incident energy, okay, is equal to 3 to 5 times the energy of the electron which has to be knocked out from the particular level, okay, then the probability for this process to occur is quite high. Okay. That is what essentially is being plotted here as the over voltage versus, okay, the yield which is going to take place. Okay. And here you can make out that as a function of over voltage, if you look at it, at some particular energy, that is the value of over voltage, it has reached a maximum value, then it comes down, then it remains almost independent of the over voltage. That means that irrespective of whether we use a 100 keV or a 300 keV, okay, essentially the yield is going to remain that same. Okay. That is one particular one. Another important factor which we have to consider is that when a vacancy has been created in this level and the atom is in an excited state, it comes to a ground state either by characteristic X-ray emission or by Auger emission. So, from this excited level, these are all the two processes by which atom can come down to the ground state. So, these two processes, if you try to look at it, these are competitive processes. Only one of them could occur. Okay. So, if you look at that yield, okay, for light elements, okay, the O-shape process, because the atomic number with the O-shape yield when we plot it, for the light elements the O-shape yield is very high, almost close to 1, because X-ray yield is almost becoming 0. And whereas as the atomic number increases, we can make out that the fluorescence yield is nothing but that X-ray yield, okay, that is increasing. And for K-shell ionization close to around 30 or 31, okay, this is the atomic number around which both the O-shape yield and the X-ray yield is becoming that same. Okay. So, for atomic number smaller than this, okay, the K-shell ionization O-shape yield is high. So, this is much more sensitive technique to find out the composition of the elements O-shape, whereas atomic elements higher than 30, essentially it is better to do energy dispersive analysis using the characteristic X-rays to find out the chemical composition, because the sensitivity is very high. So, especially for light elements, if you look at it, for various reasons, you know that elements less than 10, it is going to the detection is going to be very difficult for X-rays. So, O-shape detection is going to be possible. From this, what we can make out is that irrespective of whether it is a O-shape emission or an X-ray emission which is taking place, all these emission can take place only if a vacancy has been created in the core level. So, this creation of vacancy in the core level process is, as we can make out, is independent of the atomic number of the elements, or that means that when the energy loss of the primary beam is taking place, this is not that sensitive to atomic number of the elements. Because of that, we can detect light elements as well as the heavy elements, okay, with very high sensitivity. Okay. So, this is one of the advantage that yields could be used to get concentration of light elements like carbon, nitrogen, oxygen in the sample. Here the characteristic X-ray element for various elements are given in this table. Okay. Okay. What is given here is that, as I mentioned, electron with a particular energy enters into that sample. We assume that it is a one particular type of, it is a pure element like an aluminum or copper or a nickel. Okay. By various processes which are being mentioned, the electron loses the energy. Okay. The electrons which are coming out of the sample surface, if you look at it, they are monoenergetic electrons. Some electrons are coming out with the same energy. There are some electrons which have lost different amounts of energy, okay, by processes which we have mentioned. And if we try to find do a quantitative analysis of how much of the electrons which have lost energy, okay, that is what essentially being plotted, energy loss versus the intensity. Now, we can make out that this is the sort of a spectrum which it comes. This is the electrons which have not lost any energy, their concentration is very high. Then with about 20 to 50 electron volt, that is the Plasmon loss which is going to be there. Okay. This is what it shows, the Plasmon loss peak. And in fact, here from beyond this one, the peak is going to be so small that we will not be able to see it. So, it has been magnified 500 times. Now, we can see that there are many types of peaks. These are all corresponding to different absorption edges, because corresponding to K edge or L edge or M edge. Okay. That is essentially what we are able to see. Okay. Then in addition to it, there are some small peaks could be noticed beyond these absorption edges, okay, after as well as before. Okay. These also contain some information about what is the chemical state in which the atoms are existing in that sample. So, using this electron energy loss spectrometry, okay, we can get information about not only the elements which are present on the sample surface, but also what is the chemical state in which these elements are present. Okay. This is for a case of a nickel, we are showing how this spectrum looks like. The zero loss has got the maximum intensity, and then next comes the Plasmon loss, then this is for nickel M23 edge, then L edge comes, for which we can see that the gain has to be increased quite considerably to see these peaks. That means that the probability of occurrence of these peaks are rather very small. What are the ways in which that is what we mentioned so far is about what is the process which takes place. Okay. How this process can be put to use in a microscope. Okay. There are various ways in which it could be done. Okay. One way in which it could be done essentially is the electrons are falling onto the sample surface, okay, and that beam has been made into a very fine beam. In fact, if you want, we can scan that beam on that sample surface also, okay, or we can make a stationary fine beam onto the sample. The electrons which have lost various energies when they come out, okay, then at the back of that microscope we can put a magnetic sector analyzer, so that the Lorentz forces will be acting on these electrons. So, since electrons have got different energies, they will be focused to different points, okay, and this using various lenses, their separation has been magnified, and they will be following on a photodiode array, and depending upon where they come, from this we can immediately find out what is going to be the energy of these electrons. This way we can find out an energy analysis and find out what is going to be the intensity corresponds to a concentration, okay, and the position at which they occur, they tell about from which elements they are coming, okay. That is what essentially, this is the sort of peaks which we get it. So, this we can use to get information about it. Another way in which this has been used very effectively in a microscope is incorporation of a magnetic sector analyzer in the column of the microscope itself. So, if what one can make out is that this is the sample specimen in which the electron monoenergetic electrons are entering into this sample. Okay. These electrons, as it passes through the sample, various types of interaction takes place. Each interaction gives rise to some specific loss of energy. So, the electron which comes out is polyenergetic electrons which are coming on the sample surface. Okay. They are being focused using an intermediate lens, and they enter into, okay, a magnetic field sector where they are dispersed, okay, and then using different magnetic sector vectors, we can arrange the magnetic field in such a way the electron having a specific energy only will pass through the center and come back to that optic axis. That means that by choosing the strength of this magnetic field, we can choose electrons having specific energy to come through this lens, and only those electrons are going to contribute to the formation of that image on the viewing screen. That means that on the viewing screen, the image which we form, one thing which we can do it is that we choose electrons only with the electrons having the primary energy. So, all the electrons which has lost their energy, they are removed from the beam, and the electrons which has been only elastically scattered, they come and form an image on the screen. What is the advantage of it? Suppose the sample is a thick sample in which it enters, lot of these inelastic scattering processes will be taking place. Okay. Electrons have lost an energy. In a conventional sample, if you look at it, this will give rise to a poor resolution. Okay. The image quality becomes very poor. Okay. And if we remove all these electrons, then only the elastically scattered electrons are taken, and we get a much clearer picture of that sample. The same thing can happen in the case of diffraction also, because we know that when the sample is thick, okay, Kikuchi diffraction takes place, which gives rise to a uniform background on the sample surface. Okay. This background could be removed very easily by choosing electrons which are only elastically scattered, because that normal diffraction takes place only because of elastic scattering. This we can see it as an example. I have just taken with an energy filtered convergent beam diffraction pattern, okay, from a thick region of that sample. This is without any filtering. When we see, this is how the convergent beam diffraction pattern looks like. When the zero loss images are taken, that means that electrons which have lost some energy or the other, they have all been removed from the beam optical path, then we are able to get a much clear picture of the diffraction pattern. This is one. And another is electrons which have lost some specific energy, like suppose for different elements, that sample contains 2 elements, okay. They contain some carbon or they contain some nitrogen, and some carbides or nitrates are formed. We wanted to identify whether it is a carbide or a nitrate. Then what we can do essentially is that the same technique itself can be used, okay. And we know that if the primary beam interacts with that electron, to remove, in the case of a carbon, it is about I think some 270 or 273, I do not remember that value. This is what the K alpha, the energy which will be required to remove electron from a K. This is the electron energy which will be required, okay, or 277 of this order, okay. So, electrons which have lost this definite energy, okay, we can adjust the magnetic field in such a way that only those electrons enters into that optical path and form an image, okay. Then what is going to happen is that only regions which contain carbon, that will be lighted up, and that is what essentially which is being shown here in the case of a sample which contains carbon, nitrogen, okay, oxygen. We can immediately make out that these are all the regions which contain carbon, I think it is in a steel, and these are all the regions which are rich in nitrogen. These are all the regions which are contains oxygen, okay. This is the composite picture which shows giving different color code. Yeah, this is essentially in a silicon carbide stroke silicon nitride, okay. So, how the carbon, oxygen, nitrogen are distributed on the sample surface, that information we can get it. And another important factor which one should remember in the case of a sample is that I mentioned that looking at some of these peaks which are occurring very close to the K edge, okay, we can find out the chemical state. The shift in chemical state is going to be extremely small, of the order of a few electron volt. Because of this, if the primary beam itself has got a high energy spread, we will not be able to measure these shifts very accurately. That is why in this case, okay, using primary beam having primary beam as monochromatic as possible is required. And as we have talked about in an earlier class, we have mentioned that for Schottky FEG, okay, the spread in energy is about 0.7 electron volt, and for cold emission FEG, it is about 0.3 electron volt. So, the energy spread is very small, okay. Or if we use other types of sources like thermionic sources LAB6, we have to use some monochromator to bring down this energy spread, so that if we use energies of this order, then we can find out the chemical state of the elements very accurately. Generally, the energy resolution which can be achieved in this sort of spectrometer, the best resolution which has been achieved in this spectrometer is of the order of 0.4 electron volt is the energy resolution. In fact, we have used this microscope. Okay. Just one example which I am taking it is to find out how carbon, oxygen, nitrogen, all these elements are distributed. Okay. In a sample which undergoes what we call it as DSA, okay, that is or serrated yielding, okay, that is what we call the dynamic strain aging behavior. What is dynamic strain aging behavior? Many samples which contain light elements, okay, at temperatures which are above the room temperature, okay, and many of these interstitial elements move very fast, okay, and they can form atmosphere around dislocations, because depending upon whether these interstitial elements whether they give rise to a strain which is positive or negative, okay, they can segregate to dislocations to the strain field of the dislocation and form an atmosphere. Once such an atmosphere has been formed, it requires very high stress for the dislocation to break this atmosphere and start moving it. This gives rise to some fluctuations in the stress strain plot. Okay. We wanted to find out, because we know it is a titanium alloy which contains both carbon, nitrogen as well as oxygen, and we wanted to know which element is responsible for this segregation. But if you look at what is the region over which the segregation is going to take place, this may be of the order of 1 or 2 nanometers, okay, and that too with light elements. With other techniques it is going to be extremely difficult to identify them. Using this energy filtered microscope, okay, which is available at IGCAR Kalpakkam, and now it is also available at NML Pune, okay, we could find out that there is segregation of carbon as well as nitrogen to this dislocation, whereas oxygen is uniformly distributed in the sample. Okay. This I had mentioned about what is the effect of it in the quality of that image. Okay. There are many applications which you can think of. It is only left to your imagination to decide what sort of experiment which you should do to get the best information using this microscope. Okay. This is in a biological sample where we can enhance the contrast by removing some of these plasma energy losses. So far I mentioned about electron energy loss spectrometer. What I had given is a very qualitative picture. I have not gone into any of the mathematical this one to go into how to compute the intensity of the concentration, which is all given in most of the books and monographs which are available. You can go through them and decide how to use this technique. What is important is that I just wanted to give an awareness about these techniques which are available in the microscope. The other one is that as I mentioned, there is when a K-shell ionization has taken place, it can come down to a ground state by emitting characteristic X-rays. These characteristic X-rays can be detected using Seeley detector. Okay. This can be used to find out the elements which are present in the sample surface. Okay. In the modern day microscopes, we have special way in which these objective lenses have been designed, so that we can introduce so many detectors right as close as possible to the sample. Okay. And using these detectors we can get information about the X-rays which are coming out of that sample surface. Okay. Using these detectors, if we find out the intensity versus the energy of the X-rays which are coming out, we get some peaks. Okay. These peaks could be indexed, okay, because each peak corresponding to specific energy value, and from this we can find out what all elements which are present, and using some calibration charts which are available, we can find out what is going to be the concentration of the various elements in that sample. There are two ways in which these concentrations could be determined. One type of a concentration which is called as a absolute concentration of the elements, and another is called as a relative concentration. Most of the commercial softwares which are available in the microscope, they give only information about relative concentration only they give. They do not give absolute concentration. If we wanted to find out an absolute concentration, what we have to do is first we have to identify what all elements which are present. Then under the same identical conditions of beam current and the experimental condition, we have to use standards for various samples and find out for the identical conditions what is going to be the counts corresponding to that, and that ratio has to be used between the counts which are obtained in the actual sample to the counts which are available which are obtained from the standard sample, and this could be used to find out absolute concentration of the elements present in the sample. Okay. The same technique is being used in SEM also to find out the composition of the element. But what is the advantage of finding out the composition of elements in an electron microscope? Okay. For that we should understand that when the primary electron beam enters onto the sample, for different process, secondary electrons are coming out from some particular thickness, Auger electrons from some particular thickness, that is of the order of 1 to 20 Armstrong from the sample surface. Backscattered electrons comes from maybe about half a micron, and then the characteristic X-rays are coming from the sample about 1 to 3 micron. Not only that, the electron beam as it enters, they are getting scattered in a bulk of a sample like the way we do it in NCM, and they are getting scattered. Okay. And because of that, even if the beam, primary beam is a very focused, very fine beam, the X-rays are coming out from a region which is very large, and this decides what is going to be the resolution of the detection of, and the volume from which the composition is determined is essentially from this. So, the spatial resolution for composition detection is rather very poor. Okay. What happens in the case of a microscope? In the case of a microscope, essentially what is going to happen is that the sample itself is about 10 nanometer to 50 nanometer. So, essentially the signal is going to come from this very small region. So, though the signal intensity has reduced, but the spatial resolution is enhanced considerably, and since we are able to see the sample in a microscope, we know the region, whether it is consists only of the precipitate or whether it contains precipitate and matrix, all this information is available. Whereas in an SEM we look only at the surface of the sample, we know what is the depth to which the second phase is being present, because of which there is a lot of reliability issues regarding the composition of which we obtain from different region in an SEM. That issue is reduced considerably in the case of a TEM. And another is that the composition, as I mentioned, we can find out the composition using, that is, if two elements have a composition Ca and Cb, and that peak height ratios are here, copper and zirconium peak height ratios are Ka and Kb. Okay. When we look at the intensity of the peak heights, okay, that determines on various factors. Okay. One, what is the probability of emission of a creation of a vacancy in the K level, and what is the probability of an X-ray emission. Okay. And when this X-ray is being emitted, it comes out from the sample surface without losing energy from some particular depth. Okay. Then depending upon the incident energy, there are many other corrections, ZAF corrections, that is for that absorption, fluorescence, all these factors which has to be taken into consideration, which you might have studied in the case of EDS analysis used in SEM. Okay. Those things have to be taken into consideration. Okay. All these factors are put together into a factor which is called as a KAB. Okay. This is called as a Cliff-Lorimer correction factor. This has to be used, and this is available in many of the softwares which are provided, and these factors also can be experimentally determined. How it is to be done, this is beyond the scope of this lecture, and I am not going into that, which you can look into the literature and you will be able to get this information. Okay. most of the time the concentration which we determine using the standard softwares are essentially the relative concentrations. Okay. And since the beam can be made into a very small beam, the primary beam can be made to move on that sample surface. Suppose we assume that there is a grain boundary is going to be there. When this beam is being scanned across it, we will be able to find out how the composition varies across the grain boundary. This is one aspect which has been covered in this one. So, it is suspected that there is some segregation which has occurred onto the grain boundary. Okay, this is the scanning transmission electron microscope, the image has been taken, and then an analysis has been done on this sample which contains nickel and molybdenum, both have segregated to this boundary. Okay, this is essentially a qualitative picture, and then we can get some quantitative information also about how the elements are distributed. This is another example where we have very fine precipitates are seen. Okay, these precipitates are suspected to be, this is in an Inconel 625 alloy, okay, where it contains nickel, chromium and molybdenum. So, we wanted to find out what the composition of these precipitates. Using energy dispersive analysis, then we could find out what that composition is. Here the composition has been determined, absolute concentration has been determined, for which some standards have to be prepared. These things, as you plan an experiment, you will come to know of what all precautions which you have to do and how you have to go about. That part of it is not beyond the scope of this lecture, so I do not go into the detail, using which we can find out the composition of these phases, and using diffraction we could find out what is going to be the crystal structure. Okay, this information could be used to find out what the stoichiometry of this compound. This is essentially Ni2 with CRMO. Okay. And this is something which is very important. What is essentially is being shown is that in the EPMA or in SCM, okay, the excited volume is very large, though this is the beam size, this is the size from which the signal is coming. Okay. Suppose we wanted to detect some element with concentration, the direction limit is 0.01 percentage. If that is what it is going to be, the number of atoms which are going to be there of that element is going to be 3 into 10 to the power of 6 atoms. Okay. This is in an atomic that is analytical electron microscope, where the beam size is 10 nanometer and the sample thickness is 100 nanometer. If you look at the excited volume, because you can make out that though here the resolution is poor, here the spread is rather very small, okay, because it is only a very small thickness feature, because though the beam can come and enter 1 micron volume it can excite, the actual sample thickness is only 100 nanometers. Here the excited volume is 10 to the power of -3, even with a thermionic source about 300 atoms, okay, are going to be present, which will give rise to 0.01 percentage, okay, the reduction limit. If we do with the probe corrector, that is where spherical aberration has been corrected, okay, with a field emission gun, we can make the beam size 1 nanometer, the sample size is 10 nanometer, then excited volume is very small, and this percentage corresponds to essentially detecting a single atom. Okay. In fact, using yields, single atom identification is possible in the microscopes. Okay. But what is essentially important is when we look at the peaks, especially with respect to the energy dispersive analysis, when we are looking for the characteristic X-ray peak, what is very important is that when should you decide that the peak is significant. That is, if the intensity of the integrated intensity of the peak is 3 times the square root of the intensity of the background peak, then only we can see that it is significant, statistically it is significant, and that peak has to be considered in the analysis. Sometimes to get this we have to do either a lot of experiments, repeat the experiment, or do a counting for a very long time. Okay. And the error which is going to be associated in that sample also, which I think in standard statistics everything is given, you can find out that with 99% confidence limit. If you wanted to talk about, it is essentially if n is the total number of counts, then it will be 3 by root n into 100%. Okay. So, here I am just showing that how the spatial resolution essentially is getting reduced because of the beam scan, even the beam size. Okay, as the sample thickness becomes smaller and smaller, okay, it has got a better resolution. Okay. Another information which we can get it is using this technique, we can get information about the alchemy, that is atom site location in that sample, which atom occupies which location in the material. That information also could be used, can be obtained using energy dispersive analysis. We will stop here now. Essentially what I have done is that I had tried to give a brief idea of the energy loss spectroscopy and EDS energy dispersive spectroscopy using characteristic X-rays, which are available in atomic not atomic analytical electron microscope. Thank you.